Hi, good morning. In the last class, we have discussed about inner product spaces. Also, we have discussed the definition of norm and properties, uh, etc. Okay. Today, we are going to discuss orthogonal sets and orthonormal sets and some examples. Okay. So now, what do you mean by an orthogonal? Two vectors, let alpha and beta be vectors in an inner product space V, then we call alpha is orthogonal to beta if inner product of alpha and beta equal to 0. If inner product of alpha and beta equal to 0, then we call alpha is orthogonal to beta. As similarly, vice versa, beta is also orthogonal to alpha. Okay, so in this case, we usually call alpha and beta are orthogonal. Okay. Now, if S is a set of vectors in V, then S is called an orthogonal set provided all pairs of distinct vectors in S are orthogonal. If all pairs of distinct vectors in S are orthogonal, then we call S is an orthogonal set. Now, moving to next definition, orthonormal set. Now, what do you mean by an orthonormal set? Uh, this is an orthogonal set together with the additional property norm of alpha equal to 1 for every alpha belongs to S. So S is called an orthogonal set if inner product of alpha and beta equal to 0 for every alpha and beta in S also, for every distinct alpha and beta in S also, inner product of alpha and alpha, that's equal to norm of alpha square, which is also equal to 1. Okay, norm of alpha equal to 1 or norm of alpha square equal to 1. Okay, in that case, we call S as an orthogonal set. Now, we know that inner product of 0 and alpha equal to 0. This is a property of inner product. Okay, so 0 vector is orthogonal to every vector in V. And this is the only vector with this property. Okay, so if there is some beta such that beta inner product of beta and alpha equal to 0 for every alpha belongs to V, what's the meaning of that? Beta must be equal to 0. 0 vector is orthogonal to and this is the only vector with this property. So for inner product of beta and alpha equal to 0 for every alpha belongs to V implies beta equal to 0. Already we have discussed this property. Okay. Now, standard basis of, now one example of orthonormal set, standard basis of either Rn or Cn is an orthonormal set. It is orthogonal, also norm of alpha equal to 1 for every, norm of Ei equal to 1 for every Ei. For this, we are considering particular case, that is V equal to R3 or C3 in V. Okay, E1 is E2, E3 equal to, this is the basis, standard basis, inner product of E1, E2, what is actually inner product X1, X2, X3, Y1, Y2, Y3, X equal to this one, Y equal to this one. Inner product of X and Y is equal to X1, Y1 plus X2, Y2 plus X3, Y3. This is the inner product. So inner product E1, E1 equal to 0. Here inner product E1, E3 equal to 0. Inner product of E1, E1 is equal to 1. Inner product of E2, E3 equal to 0. Now the set E1, E2, E3 is an orthogonal set also in what is norm of E1, inner product of E1, E1 square root which is equal to 1. Similarly, we can prove inner product of norm of E2 and norm of E3 equal to 1. This implies that set is an orthonormal set. Now the next, the vector xy in R2 is orthogonal to minus yx in R2 with respect to standard inner product. If we find their inner product, that we'll get minus xy plus yx which is equal to 0. Therefore, xy is orthogonal to minus yx. Here is another example. If V is a vector space of continuous complex valued functions in the interval 0 less than or equal to x less than or equal to 1 with the inner product defined like this. And then suppose f n x equal to this one and the g n x is equal to this one. then 1, F1, G1, F2, G2, etc. is an infinite orthonormal set. Okay, this we will prove. This I will give a seminar. Okay, just note this problem. Okay, now moving to one theorem. This is very important theorem. An orthogonal set of non-zero, must not non-zero vectors is linearly independent. Very important result. Orthogonal set. Okay. So let S be a finite or infinite orthogonal set of non-zero vectors in a, with given inner product. So suppose alpha, alpha 1, alpha 2, etc. alpha m are distinct vectors in S such that we have to prove this alpha 1, alpha 2, etc. alpha m are linearly independent. So what we have to prove? We have to prove C1 alpha 1 plus C2 alpha 2 plus etc. plus Cn alpha n equal to 0 implies Ci equal to 0 for every. That is what we have to prove. For this, we know that inner product of 0 and alpha k is always equal to this is equal to 0. So for this 0, you replace C1 alpha 1 plus etc. plus Cm alpha m. Okay. You now apply linearity property C1 alpha 1 inner product of C1 alpha 1 and alpha k, inner product of C2 alpha 2 and alpha k, etc. inner product of Cm alpha m and alpha k. And from this, okay. But alphas are orthogonal. Therefore, this term is equal to 0, this term is equal to 0, and the remaining term is Ck, inner product of alpha k and alpha k. But inner product of alpha k and alpha k is norm of alpha k square. Therefore, Ck norm of alpha k square equal to 0. From this, we get Ck equal to 0 because alphas are non-zero vectors. Therefore, norm is always not equal to 0. This implies Ck equal to 0. Thus, we get C1 alpha 1 plus C2 alpha 2 plus etc. plus Cm alpha n equal to 0 implies Ci equal to 0 for every n. This implies alpha 1, alpha 2, etc. alpha n m are linearly independent. Therefore, we have choose some vectors in the set S. That means, in general, S is linearly independent. Now moving to a particular case, let alpha and beta be two non-zero vectors in an inner product space and let inner product of alpha and beta equal to 0. Then show that alpha and beta are linearly independent. This is a particular case of this theorem. This is a general case. Okay. So here also we suppose C1 alpha plus C2 beta equal to 0 and we have to prove C1 equal to 0 and C2 equal to 0. Here if you take inner product of 0 and alpha k, then we get Ck. If you take inner product of 0 and alpha 1, then we get C1 equal to 0. Inner product of 0 and alpha 2, then we get C2 equal to 0. Okay. Similarly, we know that inner product of 0 and alpha equal to 0. And for 0, you replace with this one, linearity property. And finally, we get this one. Okay, C1 equal to 0. Now, for getting C2 equal to 0, here we consider inner product of 0 and alpha. Now consider inner product of 0 and beta equal to 0. Again, apply the linearity property and we get in C2 into norm of beta square equal to 0. Each vectors alpha and beta are non-zero. Therefore, norm of beta not equal to 0 implies C2 equal to 0. Thus, we get C1 alpha plus C2 beta equal to 0 implies C1 equal to 0 and C2 equal to 0. This implies alpha and beta are linearly independent. Okay. Now, moving to last session, one corollary. This is very easy. If a vector beta is a linear combination of an orthogonal sequence of non-zero vectors alpha 1, alpha 2, etc. alpha m, must not, beta is a linear combination of orthogonal sequence of non-zero vectors alpha 1, alpha 2, etc. alpha n, then beta is a particular linear combination. This one we have to prove if beta is a linear combination of alpha 1, alpha 2, etc. alpha m, where alpha is our orthogonal sequence of non-zero vectors, then beta must be of this form. Okay, so yeah, suppose beta equal to C1, etc. plus Cm alpha m. That means beta is a linear combination of alpha 1, alpha 2, etc. alpha m. So what is inner product of beta and alpha k? This is inner product of C1 alpha 1 plus etc. plus Cm alpha m and alpha k. Apply linearity property Then each alphas are orthogonal, therefore inner product of alpha 1 over alpha k equal to 0. All inner product of alpha I over alpha k equal to 0 for every I not equal to k. So if I equal to k, we get ck into norm of alpha k square. Now product of alpha k and alpha k, which is equal to norm of alpha k square. But alphas are non-zero, therefore norm of alpha k is not equal to 0. Okay. Sorry, there is no need to write this. Okay, okay. That means in a product of norm of alpha k is not equal to 0. Thus we get ck into norm of alpha k square is equal to inner product of beta and alpha k. Here we are taking beta. In earlier case, this is equal to 0. Okay, here we are taking beta equal to this one. In a product of beta. Then from this we get ck equal to in a product of beta and alpha k divided by norm of alpha k square, as alpha is non-zero. This norm is not equal to 0. This ck is well defined. Therefore, beta equal to C1 alpha 1 plus etc. plus Cm alpha m, which is equal to sigma k equal to 1 to m Ck alpha k, and replace this Ck with this one. Inner product of beta and alpha k divided by norm of alpha k square into alpha k. Thus, we get if beta is a linear combination of non-zero orthogonal vectors, then we can write beta as like this. This is very important result. Beta equal to sigma k equal to 1 to m inner product of beta and alpha k divided by norm of alpha k square into alpha k. Once again, read the statement of the corollary. If a vector beta is a linear combination of a orthogonal sequence of non-zero vectors, okay, alpha 1, alpha 2, etc., alpha n, then beta we can write like this. So if beta is a linear combination of orthonormal vectors, then beta you can write like this: sigma k equal to 1 to m inner product of beta and alpha k into alpha k. Okay, that's all for today's class. In the next class, we will discuss about Gram-Schmidt orthogonalization process. Okay.